So for a long solenoid, now that means that if you have this guy that is, let's say, coiled up and that's pretty long, let's say it's where the length is L, yeah? This length, the coil length is L, then the B field inside is approximately given as this, yeah? We don't have to derive this. Technically, you can use the Ampere's law to derive this, but let's not go ahead and derive this, yeah? So in this case, since it's coiled like this is going to be, let's say, the length after coiling, that's very important, yeah? The length after you coil, it's not the length of the wire. After you coil, it's going to be very small, and that length is going to be L. And if I define this to be my z-axis, the B field is in the z hat direction. I see that my B field is going to be mu Ni over L. Because for every loop, right? For every loop, you're going to have mu I over L. But then you have n such coils. So you multiply by n. Because the B gets added superposition value of his works. So B gets added up. So now we want to find the inductance L, right? This inductance L is the total magnetic flux that cuts the loop over the current that produces it. So we always see that the source is here. This guy is the source and this guy is the effect. So this guy is the source. So that current is causing the B field. So now this inductance, we need to know what is the flux because of this B. Yeah? What is this flux going to be because of the B field? So for that, let's see what is the flux that cuts through one such coil, one such loop. This is loop 1. So if I were to go ahead and zoom that guy in, what I see is a loop like this. And then there is the so-called B field, which I will change it to the blue color, and all these are going to be in the z hat direction. So this is going to be my z direction here compared to the previous slide. So these are my B field all in the z hat direction. And then to find my ds, so my ds is going to be that small little surface here, ds, and the normal of ds is in the same direction as b hat, and that is also in the z hat direction. So notice that my B is in the z hat direction and the ds is also in the z hat direction. All right. So z dot z, you guys know what is z dot z? By now you should know it should be equal to 1 la. All right. So that becomes mu Ni. This integral over this entire loop is going to be the total surface area. This S is going to be the loop area. This is the coil length. L is the coil length. That means this guy is the coil length, and this area is called as S. You can call it A or you can call it S. It doesn't matter. So far, so good, guys. So that's the flux that is cutting through a single loop. One loop of this that you have zoomed in here. So now, right, we need to find the total flux that cuts through this coil, the total flux. How do we know that? If there are n such loops, then the total flux is going to be simply n times the individual flux. The total flux is going to be n times the flux cutting through one loop. So this is capital phi, yeah, this is the total. This is the capital phi and this is the small phi m. Small phi m is per loop and capital phi m is the total flux. The self-inductance is then this guy over the current, and you notice that it is mu n square S over L. The S again is the loop area, n is the number of loops, and L is the length of the coil. So very, very important. Yeah. So this mu is like permeability. Yeah. So that mu by right is mu r mu naught. Yeah. If it's the question, if the permeability is directly given, you use mu. If mu r is given, which is dimensionless, this is Henry per meter. That's the unit of this guy. Then you have to multiply it by mu naught, which is 4.10 to the power minus 7 Henry per meter. So mu r can be, for example, steel of 1000 over. So what do we mean by this mu r? That depends on the core, the so-called core material, magnetic core or any core that you would use, that if you put it inside the coil, in this case it's air core, but if I put something as a bulk material like that, like a cylindrical or rectangular core, then that can have a magnetic core. It can be magnetic core. So you can either have air core, in this case, mu is equal to mu naught, or you can have a magnetic core where in that case mu is mu r mu naught. So you have all those parameters, so you can figure out the inductance, the B field, and the total flux. Yeah. So that's pretty much about inductance law. So how much is the flux that is cutting through, the total electric flux that is cutting through all the coils over the current that produces it.